Hello, Internet. So here we have an Atwood's machine. It's a pulley with one rope stretched over it, a large mass hanging from one side, and a small mass hanging from the other side. So it's called an Atwood's machine. And the goal of this problem, or most Atwood's machine problems, is to find the tension in the rope and the acceleration of the masses. Alright. So, in doing this, there's one great trick that you should use in most pulley problems, and it's to define your coordinate axis like this. I'm going to call that the positive x direction. So that looks crazy, but you'll see what I mean in a moment. First of all, I'm saying that that's positive. Well, that part's my choice, but I believe this mass is bigger, and it'll probably accelerate down. Not that it matters, but I'd like it to move in the positive direction. So, when I do a free body diagram of the big mass, which of course I should, I'm going to call down the positive x direction. See how it's pointing down that way? When I do a free body diagram of the little mass, I'm going to call up the positive x direction. See how it's up that way? And so I'm free to define these coordinates as I choose, and doing this across a pulley will help you solve the problem. Alright, so here we are. Big M has mg pointed down, and the tension in the rope pointed up. Those are the forces. Little m has little mg pointed down, and the tension of the force pointed up. So now I'll have to do my Newton's second law equations. Sum of the forces in the x direction equals big mass times acceleration in the x direction, which is equal to, if we observe the signs, that's mg in the positive direction minus t. Now for the small mass, the sum of the forces in the x direction is equal to the little mass times acceleration, which is equal to, observing the directions here, to positive t minus mg. Alright, now let's stop and reason for a moment. We know that with a frictionless, massless pulley, which is what this is, the tension in the rope will be the same everywhere. So the t in this free body diagram is indeed the same magnitude as the t in this free body diagram. Also, we have a rigid rope that won't stretch any. Okay, it's just a plain rope. So when this mass accelerates downward, this small mass will accelerate upward at the same speed. It has to. They're connected by a rope. So A will also be the same. Alright, so looking at the equations, I know my masses, the m's. I don't know A and I don't know T, but I have two equations and two unknowns, so I can find it out. An excellent way to solve a Atwood's machine problems system of equations is the method of addition. If you don't remember, the method of addition is simply adding entire equations together. Now I'm doing it because I see on this side negative t plus t will cancel out when you add. Alright, and on this side I'm left with ma plus little ma is equal to mg minus little mg. Now let's just clean up both sides a little bit. And we get that A is g m minus m over the big M plus little m. And this is the form that an Atwood's machine always takes. Now you can have slightly different variations of Atwood's machine, where one of the blocks is on a ramp, or one of the blocks has friction, something like that. But you always end up getting that the acceleration is a piece of gravity, and it's always something about a difference of masses over a sum of masses. So that's a hint that you're on the right track. So that's the acceleration. Now, to find the tension, well, we can just take either one of our equations up here, like, say, the one on the right, solve it for t, and plug our answer from here in to here. So that's how you find the acceleration of the Atwood's machine. You just plug it back into one of your equations to find the tension in the rope. Thanks.